Have you ever wondered what a really tough, top-tier generative AI system design question looks like? And more importantly, how you would actually go about crushing it? Well, today, we're going to tear one apart.
Hey everyone, welcome to a J Repo. We're about to break down a real-world GenAI system design interview question, the kind you'd get from a place like Netflix. We are going end-to-end on this, from figuring out the requirements all the way to a deep technical solution that'll get you that job offer.
Okay, let's just get right into it. Here is the beast of a question. Design a recommender for a platform with, wait for it, billions of items. Now, the two killer constraints here are, one, it has to recommend brand new stuff instantly. That's the classic cold start problem, but on steroids. And two, the diversity of those recommendations needs to be tunable. This is a genuinely tough one.
First things first, in any system design interview, the absolute first rule is you do not jump to solutions. No way. You ask questions, you dig in, you clarify the requirements. So let's break down exactly what problems we really need to solve here.
You know, it's important to understand why the old way of doing things just completely falls apart at this scale. First up, you've got the cold start problem. A new movie just dropped, nobody's seen it yet, so how on earth do you recommend it? Then there's the extreme scale. Building an embedding table for billions of items, it would be prohibitively huge, just impossibly big. So people use hashing for the less popular items, but that just leads to random collisions, where different items get mashed together for no good reason. And of course, these systems almost always just end up recommending the same popular stuff over and over, which absolutely kills diversity.
So this is a crucial step. This is where you translate all those problems into clear, concrete requirements. On the functional side, we need relevant, personalized recommendations that can handle new items and have built-in diversity. And on the non-functional side, it has to be crazy scalable, super low latency for that instant feel, and of course, have high throughput and availability. Laying it out clean like this shows the interviewer you're thinking like an architect.
Okay, let's get into the high-level architecture. To solve problems this big, we can't just make tiny improvements to old systems. We need a totally new way of thinking. We need a paradigm shift, away from searching through a giant catalog to generating the next recommendation from scratch. And this, right here, is the core idea that unlocks the entire solution. Just think about it for a second. A large language model doesn't search a database for the next word in a sentence, right? It generates it based on the context it's already seen. So what if we could do the exact same thing for recommendations? What if we could just predict the next movie a user wants to watch, just like predicting the next word they want to read?
This thinking leads us to this really elegant three-step generative architecture. First, we need a totally new way to represent our items. Instead of just a random ID number, we create what's called a semantic ID. Think of it as a unique, meaningful word for each item, built from its content. Second, we take a user's watch history and treat it like a sentence made up of these item words. And third, we use a powerful transformer model to read that sentence and then generate or write the next word. And that word is our new recommendation.
So the whole system really hinges on this one revolutionary concept, the semantic ID. This is the secret sauce. So let's do a deep dive, because understanding this is what makes this whole generative approach even possible.
So what exactly is a semantic ID? Well, it's not just some random number. It's a sequence of tokens, kind of like a coordinate, say 712. And it's not random at all. It's generated directly from an item's content, like its title, its description, all that good stuff. This means the ID itself actually carries information about what the item is.
And this quote from the original research paper that proposed this, called Tiger, just captures the idea perfectly. They said, "We want to develop a language for IDs to represent items." They weren't just assigning numbers, they were creating a whole new language where the ID itself has semantic meaning.
So how do we actually make one of these? It's a really clever process. First, you take all the item's metadata, title, description, and you turn it into a single vector, a point in meaning space. Then, a model compresses it. Now here's the magic. The system finds the closest code word from a limited vocabulary to represent that point, but it's not a perfect match. So it then finds another code word to represent the error from that first step, and then another code word for the next error. It's this coarse-to-fine process that gives us our final sequence of tokens, the semantic ID. And this right here is why this is such a game changer. A traditional ID, just a random number. A semantic ID, it's meaningful. So when traditional IDs collide because of hashing, it's just random noise. But when two semantic IDs are similar, it's because the items themselves are semantically similar. That is huge.
It means we can generate an ID for a brand new item on the fly, solving the cold start problem. And instead of that billion item embedding table, we only need a small vocabulary for our tokens.
Okay, let's move on to the actual engine of this system. Now that we have our language of semantic IDs, we need an author that can write with it. And that, my friends, is where the transformer model comes into play.
The transformer's job is actually pretty simple to state, but it is incredibly powerful. It just looks at the user's history, that sentence of past semantic IDs, and it predicts the most likely next semantic ID, generating it one token at a time. It's literally writing the next recommendation into existence.
So the big question is, does this radical new design actually work? Let's look at the payoff. How does this architecture actually meet all those demanding non-functional requirements we laid out way back at the beginning?
Now this is where it gets really interesting, because we've got hard data. This chart, straight from the Tiger paper, compares our generative method against a state-of-the-art baseline. If you look at NDCG at 5, which is a key metric for recommendation quality, the baseline scores a 0.0244. Our Tiger method, it gets 0.0321. That is a performance uplift of over 30%. So this isn't just a cool idea, it's a flat-out, better-performing one.
Okay, so it's more accurate. That's awesome. But what about that other really tricky requirement from the interview question, the tunable diversity? How does this architecture give us control over that?
Well, because our model is generative, we can use a standard trick from language models called temperature sampling. Just look at this data. At a temperature of 1.0, the entropy, which is just a way to measure diversity, is 0.76. But if we crank that temperature up to 2.0, the model gets more creative and the entropy jumps all the way to 1.38. This gives us a simple, elegant little knob we can turn to dial the diversity up or down. We've just solved the second killer requirement.
All right, so you've just laid out this entire system. Let's zoom out. What is the interviewer thinking right now? What signals did you just send them? And what are the common mistakes you just totally sidestepped? This is the metagame of the interview.
When you present a solution like this, you send some incredibly strong signals. It shows you think from first principles. You're not just repeating something you read. It shows you get the trade-offs between old and new methods. You're future-aware, using a truly cutting-edge approach. And you're data-driven, using actual metrics to prove your design works. This is an absolute A+ answer.
And just as importantly, this approach helps you avoid all the classic traps, jumping to a solution without asking questions, talking only about a model instead of the whole system, ignoring the hard stuff like scale and latency, and, a big one, failing to explain the why behind your choices. This structured thinking is exactly what they're looking for.
So if you remember just one thing from this entire breakdown, let it be this. The fundamental paradigm here is shifting. For a massive class of problems, recommendation is no longer about searching a giant index. It's about understanding context and generating a response. It's a language problem now.
All right. If this breakdown helped you think about system design in a new light, do me a favor and hit that like button and subscribe to AJ Repo for more deep dives just like this one. And I really want to hear from you. Drop a comment below with the toughest, most out there interview question you have ever been asked. Let's see what we can crack open next.